This brings us to the topic of convection. Convection is a transfer of heat by mass movement within a substance. This can only take place in fluids where atoms and molecules are free to move about, such as in the case of boiling water presented here. Because air is a poor conductor and a poor radiator, most of the energy transfer is the result of convective transfer. So here we have a radiative surface, be it a hot coil in the case of an electric stove, or an induction surface in the case of an electrical induction stove. Now that works on a different principle where the magnetic field reversal generated in a steel pan or an cast iron pan is transferred through conduction to the water molecules at the base of the pan, right at the interface between the pan bottom and the water above. If that water becomes hot enough, it could flash to steam, and in changing phases, these little steam bubbles that are created are going to become much more buoyant than the surrounding fluids. They're going to rise. As they rise, they entrain other liquid along with them, and that brings us into this boiling situation where the water is overturning because of conduction between the metal surface and the water, and convection, the movement of the water above. The net result is water vapor above the pan that has absorbed an enormous amount of heat. That heat is not lost during this process of the conversion from liquid water to vapor. We've gone through a phase transfer or a phase transition from liquid to gas. That's going to result in a gas with a lot of stored heat. That's known as latent heat, and it's going to come back at some point. It's not lost. One way to think of it is the way a lava lamp circulates. And we'll take a look at that here. Now in this video, we're taking a look at a lava lamp. This is a mixture of a proprietary fluid here, which has about the same density as this wax. When the wax sinks, it gets heated up on an electric coil, and the decrease in density, like a Remax balloon, sends it up into the skies of Saskatoon. When the wax in that lava lamp begins to cool at the top, it becomes more dense and it returns to the base of the lava lamp to undergo regeneration. So this isn't quite a phase change, but it's a definite density change. So the blob rises to the top, cools off, and then sinks. The opposite is an insulator. Insulators are poor conductors. Air is a very good insulator. It's cheap. Therefore, conductive heat transfer is not considered significant in meteorology. Most commercial insulators are made up of a substance with lots of little air bubbles, trapped air in the case of polystyrene. Now, styrofoam is a trade name. It's a commercial product. Expanded polystyrene is what most of us work with on a regular basis. Now, over here on the left, we have a typical inexpensive polystyrene cooler. These are the kind of coolers that my students would always buy in field school, and I would tell them that you could spend a few dollars and get one of those things right now. You're going to put your food in there, and your food is going to become a blend of different types of food that is all going to leak out of the broken cooler, which is going to begin leaking in about 10 minutes. You could spend a little more money, invest in a Yeti. In this case, I think they got ripped off. Or upgrade to a plastic-coated, extruded, or expanded polystyrene cooler here. If you really want to go high-tech, at least most of you have probably heard the term nature abhors a vacuum. That's attributed to Aristotle. Nature doesn't really abhor a vacuum. There are actually many benefits to vacuum for our purposes. Here's one example. This is a 36-ounce Rambler. I picked one of these up about I think 3 years ago in Colorado at some motorcycle dealership. When my friend had a flat tire, I saw these things were on sale, 50% off, why not? What's really cool about this is you can fill it with ice water and it will remain as ice water for about 5 days. I tried that out. It stays really cold for a really long time. And that's because there aren't little bubbles of air in here in this jacket. It's an evacuated stainless steel tube essentially. So we've removed the air to eliminate the tiny bit of conduction that could happen if there was air within the walls of this container. The opposite extreme here, another set of vacuum tubes. In this case, we have a small copper tube running down the middle of this vacuum tube, which is made of glass, that's coated with a black aluminum compound. We won't worry about that right now. This black aluminum compound is very effective at absorbing incoming radiation of all wavelengths and re-emitting that radiation at a longer wavelength, in this case as infrared radiation that is then picked up by this manifold and sent off to either heat your house or generate hot water for your house. These are very effective at heating a home at any outside temperature. They work just as well at minus 40 degrees as they do at plus 40 degrees. Latent heat that is released or absorbed during the transition from one phase to another, whether it's a gas phase to a liquid, liquid to a solid, or solid to a gas, means that there's a lot of energy in a cloud. We can see that here graphically, where we're going to start out with some ice at minus 40. So typical winter day here in Saskatoon, walking into school, something we used to do. At minus 40, the ice you're walking on could be heated up. We add some heat to that ice from minus 40 to 0. We don't have to add very much heat to get from minus 40 to 0. Just a little bit of heat energy will do it. The ice remains ice up to that point. Then something kind of magical happens at 0. We begin the phase change. So we're transitioning from a solid, ice, to a liquid, water. This water is going to absorb a large amount of heat to make this change from 0 to very slightly above 0. And this is the latent heat of melting. We added a large amount of heat to this ice to change its phase from solid to liquid. And this is why we use ice cubes in drinks. The ice has to absorb an enormous amount of heat. Therefore, it tends to keep the drink much colder than it would be without that. You may have seen these things called Scotch rocks advertised. They're basically chunks of rock that have been polished, and they're supposed to keep your drink cold without diluting it. Problem is, we don't go through a phase change, so very little energy is exchanged here at the low temperature end. Basically, you're putting your drink in an extra thick glass. That's really all those Scotch rocks do. Now we have liquid water. We're going to heat that water from 0 to 100 degrees centigrade. In doing so, again, we're adding energy. We're adding a specific amount of energy, 1 calorie per gram per degree. So we add 100 calories to get 1 gram of water to 100 degrees centigrade. Now again, something magical happens at 100 degrees. In this case, we're changing phases from a liquid to a gas. We're going from water to steam. This takes an enormous amount of energy, which is why we have to put a pan on a stove and crank up the heat. We're adding energy to that water. For every gram of water, we're going to add an enormous amount of heat that is going to be stored in that water as it changes into a gas. Now that gas is free to leave the area, ultimately becoming a cloud perhaps. When it becomes a cloud, it's condensed, it's changing phase back to liquid, and it's going to give off all of this heat that was absorbed in turning it into a gas. If that liquid then falls from the sky, that heat remains in the sky, the water goes back to the ground as a liquid or a solid, and the whole process starts over again. So there's a very, very large amount of energy, amount of heat stored in a cloud. Whenever it rains or snows, any precipitation event, this latent heat is given off back to the air. This explains why it's very easy to calculate the nighttime temperature of a given area. Say Saskatoon, we can calculate that very easily using the calculator in your phone. How low is the temperature going to get tonight? So you need to know a couple of things. What is the temperature now? What is the humidity now? If you know those two things, you can determine how cold it's going to get tonight, because we're relying on these phase changes and the amount of heat given off to define that temperature. It's known as the dew point, when vapor turns into dew or turns into liquid on grass or a metal surface, really anything that's sitting outside slightly cooler than the air. So as that air cools down and condensation begins, heat is given off. The more condensation that occurs, the more heat that's given off. So we've reached the dew point. The temperature can't go below that unless something else in the atmosphere changes. That's kind of neat. So how do we move this heat around? We have convective circulation, a turnover of the atmosphere because of relative density. We've seen that in the lava lamp, the wax that doesn't change phase really, but it changes density. We can do that with a hot air balloon. The Remax balloons or the slot machines you see flying around town in the summertime that make my dog crazy, those fly because of a change in density, essentially like convective circulation. The density of the air in the balloon is low because it's hot, and it rises because of this density difference. Our examples are boiling water and lava lamps. Advection is a different way of moving heat. This is the horizontal component of convective flow, and we call it wind. One way to experience this is to go outside in the winter, where you can really feel the airspeed. If you go out without a coat, you can feel it removing the heat energy from your body, taking all that energy, which brings us to the greenhouse effect and the physical causes. Greenhouse gases, by definition, absorb or emit infrared radiation in two different ways. They can change the rotation rate of molecules, and we can see that here. We can add radiation, in this case infrared radiation, to a water molecule, and that's going to increase its rotation rate. It's going to speed it up. That rotation rate is a function of the energy in this system. So as we increase the energy, we increase the rotation rate. Increasing the rotation rate increases the heat content, and it increases the temperature. Turning to the basketball analogy, the spinning of a basketball on your finger is going to be very similar to the rotation of a molecule in the atmosphere. If that molecule is rotating at a specific rate, which you can see here, and we want to increase that rate of rotation, increase the heat energy stored, you add energy at a specific wavelength. That's the same way greenhouse gases work. They hit certain molecules at just the right rate to increase their vibration or their rotation. Now, how does this affect the absorption of radiation? Here we see the water rotation band, 12 microns and longer wavelengths. Almost all of the infrared radiation of 12 microns and longer is absorbed. So this band extends in the microwave range of wavelengths, which is why microwave ovens work, why they heat our food up. So we can see here, wavelengths on the x-axis in microns and absorption percentage on the y-axis. So you notice that certain wavelengths are very effectively absorbed by different molecules, water molecules, CO2 molecules, ozone here, and etc. We throw the other greenhouse gases into this mix. An example, a real-world example, is putting a pizza in a microwave. The water-rich sauce is going to heat up far more than dry portions of the pizza, the crust or the cheese. But there's a little bit of a twist to that, which is kind of cool, in that the liquid water is going to be very sensitive to microwave radiation, microwave wavelengths. Very sensitive to that. It's going to become excited. When water becomes ice, it's changed its phase. The orientation of the molecules relative to one another is different. It's no longer very sensitive to microwave radiation. So when you're heating something up from frozen to edible to hot, what you're doing is heating up portions of it. Once they become liquid, they can become very, very hot, whereas the water that remains in the ice phase isn't really affected by those microwaves. It's going to take the hotness of the water around that ice to melt that ice rather than the microwaves. So this is why you might bite into something that's blazing hot on the outside and frozen on the inside. This reminds me of something we saw a little bit earlier. This diagram that we talked about earlier, the Wien's displacement law diagram, where we have insulation striking the outer atmosphere here, and we have insulation reaching the Earth's surface here. You notice these dips. We talked about these briefly before. What these are absorption bands, and they're absorption bands from various gases, various substances in the atmosphere. When gases absorb incoming radiation, we see a reduction in the amount of radiation that reaches the Earth's surface that can then be absorbed as blackbody radiation, converted into longer wavelengths, and then re-emitted as blackbody radiation. Another way that molecules can absorb or emit infrared radiation is by changing the amplitude of vibration. If the frequency of the wave is correct, it'll increase the amplitude of vibration. So again, this type of bending, this spring action of a molecule is going to be sensitive to particular wavelengths of radiation, insensitive to others. So one model you can look at is what's called a simple harmonic motion model that is pretty similar to this. So again, we're going to take a center object here and two nodes to the right and to the left, and these are going to flex upward and downward. If we're inputting energy at the right wavelength, it's going to increase the rate at which these nodes are going to move around the center, around the axis here. At 15 microns, CO2 strongly absorbs infrared radiation. Water vapor also strongly absorbs infrared radiation at this wavelength. This is something that's going to increase the temperature of the atmosphere because it increases the vibrational frequency of the water molecules in the atmosphere, or in this case, of the CO2 molecules in the atmosphere. We have an example here, nitrogen. Water vapor and CO2 are going to be the most important greenhouse gases in the Earth's atmosphere, but methane is important, nitrous oxide is important, ozone, freons also very important. Again, greenhouse gases are excited by certain wavelengths, and they respond by increasing their rotational velocity or increasing their vibrational frequency. When we look at clouds are one of the more confounding aspects of the Earth's climate system. In terms of mathematics and climate models, it's very difficult to make a cloud. Once you've made a cloud, it's very difficult to get rid of that cloud. Again, mathematically. We can observe it by going outside on pretty much any given day. It's easy to see, but it's hard to visualize in terms of a computer model. And here's an extreme exaggeration of clouds around the planet Earth, something a little more realistic here. In general, clouds cover about 50% of the Earth's surface at any given time, so they are very important. They are white and shiny, as we can see here off the coast of South Africa. So they tend to reflect incoming radiation. Once the radiation is in contact with the Earth's surface and re-emitted as longer wavelengths, these same clouds serve to contain that radiation, to block it below the cloud, as opposed to reflect it from above the cloud. We have a couple different types of clouds that are the atmosphere's response to the conditions. Here we have cumulus clouds. These are the cotton ball-like clouds we commonly see in the summertime. These are globular individual cloud masses. And normally they're going to have a flat base, because that's where vertically the conditions for the formation end. Above, we have the puffiness. So flat bottom, puffy top. A cumulonimbus is a big version of a cumulus cloud. These are large, very tall clouds that generate potentially enormous amounts of precipitation. They generate phenomena such as thunder and lightning. They can generate hail. They can generate hurricane winds. They can do a lot of damage. Pretty spectacular clouds. Stratus clouds are a uniform layer of low clouds, frequently covering much of the sky and occasionally producing light precipitation. So these are the dreary clouds. They appear, maybe last for days. Everybody becomes gloomy. Here is an example of stratus clouds from the high latitudes. This is from Greenland, a place called Kulusuk, which is the southeast of Greenland near Amashiluk. This is a uniform layer of low clouds, again, that frequently covers the sky and may produce light precipitation. So on this particular day, there was a light drizzle. Temperature was probably around 5 degrees centigrade, or around 40-ish, 41 or so Fahrenheit, something like that. Cirrus clouds are detached high clouds, so high in the atmosphere, composed of icy filaments. These are sometimes called mare's tails because they look like a mare's tail. These clouds can have a large vertical extent. You could think of them as a snowstorm that's happening high in the atmosphere. Wispy, lacy, filamentous ice crystal clouds. When the sun hits them just right, they can produce rainbows or what are called glories sometimes. You look down from an airplane, you can see the shadow of your plane on the cloud tops with a circular rainbow around. Now here's a diagram from your book, or from the book. It shows the relationship between insolation and clouds. Don't worry about the numbers here. Again, these figures make me crazy too. Things seldom add up to 100%. The Earth's globally average atmospheric energy budget is depicted here. All fluxes are normalized to 100 arbitrary units of incident radiation. What's the takeaway here? We have our source of insolation. If it was to strike the Earth directly, and the Earth was a black surface, not shiny, not glossy, just a plain black surface, it would absorb 100% of this insolation. No clouds, no atmosphere, just a black surface perpendicular to the sun, 100% absorption efficiency. All of that energy would be re-emitted at a longer wavelength back into space. Nothing would trap it. But we do have an atmosphere. We do have greenhouse gases. We do have water vapor, which can be a greenhouse gas, and it can turn into a cloud, which has an opposite effect. So in the case of clouds, where the cloud is located and the type of cloud is going to be important. The cirrus clouds we just took a look at are high up in the atmosphere. They allow radiation to pass through pretty readily, but outgoing radiation gets reflected back to the Earth's surface from them. So they allow radiation through. The radiation strikes the Earth's surface, gets re-emitted, and they help block that radiation, help keep it in the atmosphere. It doesn't go back to space without a fight. Now, other types of clouds, like cumulus clouds, depicted here, are going to be very reflective. A lot of the radiation that strikes them is going to bounce back. Again, if you fly much and you get above the cloud tops, it gets very bright. Eventually it can be so bright that you just close your window and watch whatever horrible movie they have on. Or now we have TV shows. So you close your window to prevent blindness and shield yourself from that reflective glare from the top of these clouds. Other clouds behave variably in between those two end members. So again, they block incoming radiation usually, and they block outgoing radiation. So the time of day is going to be important for when a cloud appears or disappears, and the cloud type and the altitude of that cloud is going to be important for regulating the radiation budget, the inputs and outputs of the Earth's radiation budget system on any given day. Now here we have a diagram. It's a systems diagram. I'm not a big fan of these, but we'll go through this one. So we'll start out with surface temperature of the Earth. Now if the surface temperature of the Earth increases, we're going to see an increase in evaporation of water. We have higher temperatures, therefore we have more energy to add to surface water. When you add energy to water, you excite those molecules. They spin faster, they vibrate faster, they have more energy. They may obtain enough energy to break free of the liquid surface and become water vapor. Once they become atmospheric water, then they're free to move about in the atmosphere. They can serve as a greenhouse gas, trapping energy, increasing the temperature of the atmosphere, and in doing so, increasing the temperature of the atmosphere via the greenhouse effect, they increase the surface temperature of the Earth, which leads to more evaporation, more water vapor, more of a greenhouse effect, higher temperatures. So if nothing stops this from happening, we end up in a runaway greenhouse effect like the planet Venus, which is 460 degrees centigrade at the surface, compared to Earth, which is 15 degrees centigrade at the surface, a much lower temperature. Now, if we switch a couple of those parameters, we still have the surface temperature of the Earth here. If we increase the surface temperature of the Earth, we're going to decrease the snow and ice cover. That's what this means, an opposite effect. So the snow and ice cover are going to decrease. Snow and ice are white, generally, shiny, very reflective, and by removing that snow and ice, we're changing what's called the albedo. The planetary albedo is the shininess or the reflectiveness of, in this case, the Earth. So we reduce snow and ice, we reduce the albedo. The albedo is going to have an opposite effect on temperature here. So in reducing the albedo, we increase the temperature. So albedo goes down, temperature goes up. Temperature goes up, snow and ice go down, the albedo goes down, temperature goes up further. So again, a positive feedback loop. Okay, so getting back to the answers from a question I asked long ago, what is the proper orientation and tilt for a solar panel in Salt Lake City to obtain the maximum amount of insolation on a particular day of the year? For Salt Lake City, I calculated 40.76 degrees tilt, aimed to the south. Key West, Florida, 24.57 degree tilt to the south again. Which day of the year would this be? That's something to think about, and you can fire an answer off to the webpage here if you want.